All right, so we're going to start off by looking at section 7.5, and there was a formula we were just getting to, which was the sum and the difference of tangent. So we're not actually going to be plugging anything in. What I want to do is just look at that formula and see if we can figure out where it comes from. So let's write this a little bit more generic. How can you write tangent in terms of sines and cosines? Yep. Right. So the tangent of alpha plus beta equals the sine of alpha plus beta over the cosine. And that's how you could do this. You could do it just like that. Let's use the two identities that we know for the sine of a sum and the cosine of a sum and write that out and see if it looks anything like what we have there. Okay, when you have sine, are the sine of a sum, do you group your trig functions or are they mixed? They're mixed. So we're going to have sine, cosine, cosine, sine. And what symbol do we put between them when we do the sine sum identity? We do a plus. Yep. Alpha.
It's like part 2 of us doing that yesterday.
Yep. Divided by. And what about the cosine sum? Are they grouped or are they mixed? They're grouped for that one. So cosine, cosine. Sine, sine. What symbol do we put between the factors here? Yep, put a negative. Alpha, beta, alpha, beta. Well, that doesn't look like the tangent identity. If you look at the tangent identity, it really has kind of four terms to it. 2 in the top, 2 in the bottom. There's 1, 2, 3, 4. Which one of those 4 terms looks the simplest? The 1. So why don't we make our formula have a 1 in that spot? But let's not worry about what will happen to everything else. Let's just see if we can force this spot to turn into a 1. And whatever we do to this to make it a 1, we have to do it to all 3 other spots. So what could you do to this lower left part to make that box into a 1? Yep.
You could divide it by cosine alpha.
If you divide by cosine alpha, it would not make what's in that box a 1.
Oh, the whole thing you do divided by cosine alpha, cosine beta.
Yes, we're going to divide everything by cosine alpha, cosine beta. But we have to do it in all 4 spots. Let's see what happens. So we have sine alpha, cosine beta. Leave room to do some division. Cosine alpha, sine beta. Leave some more room to do division. And now let's write down the bottom. Cosine alpha, cosine beta. Leave a little bit of space. And sine alpha, sine beta. Okay. And what are we going to divide everything by? Cosine alpha, cosine beta. We're forcing the lower left here to look like the identity. How would you know to do that before you actually know what the answer is? You wouldn't really know. So we already kind of know what it looks like. So I'm just trying to make my answer look like what it's supposed to. Let's see what happens. So let's divide by cosine alpha, cosine beta. Everywhere. As long as you divide all of them by the same thing, that's okay. Let's start in the upper left. What happens in the upper left to start out? The what?
Your cosine betas are canceled.
Cosine betas cancel. Okay. We'll leave that for now. What happens in the upper right? Cosine alphas cancel. How about in the lower left? Everything cancels. And what about in the lower right? Nothing. Okay, so let's look at what we're left with. Sine alpha over cosine alpha. That's tangent alpha. What about sine beta over cosine beta? That's tangent beta. In the lower left, we have 1 minus, what's sine alpha over cosine alpha? Tangent alpha. And then sine beta over cosine beta? Tangent beta. And if you scroll back up and look at the formula, the tangent of the sum, that's exactly the formula we just got. So the tangent identity is really derived from taking the sine and dividing by the cosine. And you could do the same thing for a sum or a difference. If you did it for the difference, you'd have a little bit different setup, but you'd still be trying to get a 1 in the lower left. And when you divide everything by what you need to, it ends up coming out exactly the same, except these two signs are switched. That's all that happens. So that's the tangent sum identity. Any questions on that? Okay, so so I think we wrote both of these identities down yesterday, but here they are again, in case you wanted to see them. Is there any question on the tangent sum and difference? A little bit more of a pain when you do numerical stuff with them because you end up with square roots in the bottom and you end up with fractions over fractions. So you have to fix both of those issues. All right, let's take a look at this. Now, another problem we can have, besides having a sum or a difference inside your argument, because we don't want the argument to be complicated. Ideally, we want the argument to be a single thing. Nothing added, nothing subtracted, and nothing multiplied. So we want to be able to take arguments that are complicated and make them simpler. We know how to do it for sums and differences, for sine, cosine, and tangent. What we don't know how to do yet is for multiplication. What happens if you take your argument and double it? Well, you can't just take 2 and bring it in front and say, oh yeah, that works. Well, first of all, that's a horizontal transformation on the left. That's a vertical one on the right. So just from transformations, they're not the same. So you can't do that. So the question is, well, what can you do? Let's take a look. Let's see if we can figure out what sine 2x turns into. What's another way of writing 2x? And I'll give you a hint. It's going to look like an identity we already know once we do that. Yeah?
X plus X.
Right. You could write it as sine x plus x. Now, use the sine sum identity on that and see what happens. Okay, so sine of a sum. Are the trig functions grouped or mixed? Mixed. Sine, cosine. Cosine, sine. And Layla, what symbol is going to go between them? A plus. Yep. And what's my first angle that I'm filling in? What's my second angle? They're also x, so they're the same. So I have sine x times cosine x plus cosine x times sine x. What's the difference between this and that? Nothing. They're the same thing. So it's like sine times cosine plus sine times cosine. So when you combine like terms, what would you get?
2 sin x times 2 sin x.
Yep. That is what sine 2x is. It's 2 sine cosine. So I'm not going to go through and verify whether that's going to do this one, but we basically already did it. We proved that this equals that. And the way to prove it is to write that as theta plus theta and use your sine sum identity. When you put a 2 in front of an angle, you double it. Because of that, this type of formula is called a double angle identity. Double angle identities enable you to get rid of a 2 in front of an x. Unfortunately, there's no general pattern that's easy for getting rid of any number in front of x. If you know how to do it for a 2, then you can do it for higher numbers. But higher number in front of x, the longer it takes. 2s are the easiest. Higher than 2 starts to get a little bit tough. Right. So there's the double angle formula for sine 2 theta. Now, we proved that one. I'm not going to prove the cosine 2 theta, but there's several ways you can write it. So I'm going to give you one way, and then we will prove the second way. So look how much different that is, right? Just because you're dealing with cosine, it becomes cosine squared minus sine squared. Okay, let's write that down for a second on the other page. Cosine squared minus sine squared. What does that kind of look like, but it's not?
The identity that we had where it's equal to 1 is bad.
So can you tell me what identity what it is?
This is the sine squared plus cosine squared equals 1.
Sine squared plus cosine squared equals 1.
I believe so.
So that's our Pythagorean identity, and that you can prove based on the unit circle. I don't think we went through the proof on that, but I want to use this to rewrite this a different way. Let's say I want to substitute in for that. Based on the Pythagorean identity, what does sine squared equal?
1 minus cosine squared.
So sine squared is 1 minus cosine squared. Now, if you distribute your negative, what do you get?
Minus 1 plus cosine squared.
Okay. And now, combine like terms.
2 cosine squared minus 1.
Right. You could say 2 cosine squared minus 1. That is another way to figure out what the cosine of 2 theta is. It's based off the first identity, but substituting in one of the Pythagorean identities for part of it. So 2 cosine squared minus 1. I didn't show you the third way. The third way is just like the way I showed you. The difference with that way is instead of substituting in for sine squared, you substitute in for cosine squared using the Pythagorean identity. And you get something that looks kind of similar. All right, so a few different ways to do cosine 2 theta. Now, if you had to do tangent 2 theta, how could you do it with what I showed you? Yeah?
You do like sum of tangents, so you do theta plus theta.
Okay, so you could try to derive this formula using tangent theta plus theta, and then use the tangent sum formula. So we could try that. What else? Yeah?
Use sine 2 theta over cosine 2 theta.
Yeah, we could try sine 2 theta over cosine 2 theta and see what happens. Let's try it with the sum. Let's see what we get. So let's go back to it. And if we do it with a sum, and both of these are thetas, you just change everything here to thetas. And the nice thing about doing the 2 is you have 2 angles that are the same. You usually end up with a lot of like terms. What's tangent theta plus tangent theta? 2 tan theta over 1 minus, what's tangent theta times tangent theta? Tangent theta squared. So I don't remember if that's the way the book writes it, but whatever way I'm about to show you could come from this somehow, because that is correct. That's one way you could do tangent to theta. Let's see what the book had. Is that the one we did? Yeah. So you can get the tangent to theta identity using the tangent sum identity. That's exactly how they did it. So it's not really that hard to figure out where these are coming from. They're all based off more basic ones. And this one, I don't know if I've ever really gone through the proof. I'm sure you could figure that out using the cosine double angle formula. And I bet that's exactly what you would get.
Is that not what I did first?
The first one I did was the sine 2 theta.
Oh,
But yeah, I think, yes, because your sines and cosines are grouped when you do cosine sum or difference, you're going to end up with a cosine squared on the left, a sine squared on the right. And if you write this as a sum, you always put the opposite symbol between them. So yeah, that's exactly where it comes from. Cosine double angle formula comes from the sum identity. Any questions on those? All right, let's try a couple of examples. Let's try to rewrite 2 cosine x plus sine 2x only with sines and cosines. So in other words, no 2's in the arguments. No 2's inside the arguments. If I don't want to have 2's in the arguments, is that first one okay, or do I need to fix it?
Okay.
That one's fine.
Yeah.
But what is sine 2x equal?
Sine x plus x.
And then when you simplify all of that, what do you get?
2 sine theta.
Oh, 2 sine theta cosine.
Yeah, in this case, it's just x. So 2 sine x cosine x.
Right, that's the identity that we just did, right?
Mhm.
That's what that's doing.
So technically, we've done what they wanted. Rewrite that with only sines and cosines. That's exactly what we have. What they mean is no numbers in front of the x. If they asked you to rewrite it and factor it, what could you factor out of that? 2 cosine x. And what would you be left with?
Plus sine.
Wait.
1 plus sine.
1 plus sine x. So if they wanted a factored version, that would be factored. So if you have a 2 in front of a letter, really easy to get rid of. It's not that hard. Let's try a 3. And if you can do a 3, then you could probably guess what you need to do for 4s, 5s, 6s, and so on. Let's just try it with a 3, and I'm going to make it even simpler. I'm just going to do one trig function. Let's just do sine 3x. So sine 3x. Now, there probably is a formula for doing a 3 automatically. Do we know it?
No.
No. So we need to think of 3x in a different way.
X plus x. Yeah.
Okay, so that would give me a sum, but I don't have an identity that adds 3 things together. So what's another way I could think of it? But that's kind of on the right track, yeah?
2x plus x.
All right, let's think of it as 2x plus x. Now you have a sine sum identity. Let's apply that. And whenever you apply the identity, it starts to get a lot bigger. So we're going to have sine, cosine, cosine, sine. What goes between them?
Plus
Plus, what's my first angle?
2x.
Second angle? And then 2x and an x. Some of that's okay, some of it isn't. Anything that just has an x is fine. Anything that doesn't have an x, we need to fix again. So by applying the sine sum identity, you took your 3, and now you reduced it into a problem with 2's. Now let's go through each one that we need to. What is sine 2x?
Those are sine x, cosine x, what?
2 sine x cosine x.
Wait, what? Sorry, why?
That's the sine 2x identity. How about cosine 2x? We have a lot of ways we can write that one. Can somebody give me one way?
Cosine squared. No, cosine x squared minus sine x squared.
Cosine squared x minus sine squared x. Yep, we could do it that way, or we could pick any of those others. I guess we could do the top one, cosine squared minus sine squared. So, just put that down. So, cosine squared minus sine squared. And what's still next to it on the right?
Sine of x.
Sine x. So, at this point, we've simplified everything so that the x's all have 1's in front of them. But look how much more complicated it got just from having a 3 here, sine 3x, to trying to get rid of that 3. And we still have some things we can combine. What's going to happen in this first term?
Cosine squared.
What's the whole thing?
2 sine x cosine squared.
2 sine x cosine squared x. So we've got that. How about here? What do we have to do with that sine x on the outside? We have to distribute it. So we're going to end up with cosine
x sine x and then minus sine cubed x.
sine cubed x. And if you look at all of those terms, sometimes they might ask you to pull out something they all have in common. Does anybody see something they all have in common?
Cosine squared.
Nope, the last one does not have a cosine squared.
Sine, right?
Sine what?
Just sine of x.
Just sine of x. There's 3 terms here. And all 3 of them have a sine x in them. So that's the only thing we could take out. What would be left in the first term if you do that?
2 cosine squared x.
2 cosine squared x. Second term?
Cosine squared x.
So now we got some more like terms we can combine.
And
Right,
then sine
everybody
squared.
by sine x.
Nope, no division in this problem.
Wait, sorry.
Wait, it doesn't have to be squared.
Oh, squared.
Are we just combining?
Any question on factoring out the sine?
What was this? What did you just do?
I factored out sine. Because sine was in common here, here, and here. So I pulled one copy out.
How did you get 2 cosine? Because you take out the sine.
Because when you factor it out, this is gone. And you're just left with 2 cosine squared.
Oh, I thought you just left with sine.
Now, look inside the parentheses. Are there any like terms we can, yeah, we can add the cosines. What's 2 cosine squared x plus 1 cosine squared x?
3.
Cosine squared x.
Okay, so 3 cosine squared x.
Sine
So it got a little bit smaller. I don't think there's a lot more you're going to be able to do with that. I think that's pretty much it. So there's the formula for sine 3x, written without any numbers except a 1 in front of the argument. And there's probably lots of other ways to write that. I don't know what, if you just Googled it and looked it up, I don't know what it would say. But I'm sure whatever it says, as long as we did that right, we could somehow make what you get and what I got match up. Any questions on that? All right, so let's see. So this will end 7-5. We did 2 through 5 last night, right? All right, so let's just try a couple of them. Let's try. All right, 2 through 5. Let's do 1 and 7. Let's do 11. And then let's try. I'm not going to give you any that are too high. The book has some that have a 4 in front of the number. But sometimes an even number is actually easier because then you can split it up into two things that are the same, like 2x and 2x. So it's actually easier than having a 2x and a 1x. But 17 and 18, that's like what we just did in class. And then, okay, so yeah, we'll stick with those problems for 7.5. All right, so all the identities that we learned in 7.4 and 7.5, okay, to simplify something with sines and cosines, to sometimes multiplying by the conjugate, using your double angle formulas, all that stuff is basically going to be able to help us to solve trig equations. So in this section, everything we're doing, pretty sure everything we're doing, is going to be looking for a number that's an answer. So we're looking for numbers. We're not really doing proofs, like proving that this equals that. So we're trying to calculate an answer. And a few different things are going to come up that we need to remember from stuff we did before. So I'm going to go through some of the techniques we can use to solve trig equations. Okay. Here's an example of a trig equation. Don't write it yet because I haven't given you the techniques on how to solve it. But that one, I wanted to put it up because if you look at it, it kind of reminds you of a type of format you see in algebra. Does that equation kind of look like something you see in Algebra 1? If you just look at the format. Yeah? Yep, it's a quadratic. The only thing with a quadratic is all your trig functions need to be the same. Well, we can make them all the same. That part's easy. The key is you have something squared, something not squared, and a constant at the end. 3 terms on the left, like the pattern I just explained. That is a quadratic type of problem. What's one way you can solve quadratics? You can try factoring. Yep. So we might do some factoring. What's another way? If we're going to be solving analytically, that means not graphically. We might still use graphing a little bit if we get one that's really hard and we need a little help with it, but we're going to try to focus not on that. What else besides factoring? Yeah?
Quadratic formula.
Yeah, you can use the quadratic formula. And another thing that's always good to do is if you have multiple trig functions mixed in the problem, we only want to have one trig function. So how are we going to be able to change a problem that has multiple trig functions so it only has one? Identities. Any of the identities that we've learned in 7.4 and 7.5. That's really it. That's the only explanation I need to give you before we just try some problems. A couple things to remember, though, when we're solving these kinds of problems. If square roots come up in a problem and you use that to solve it, like here, how many answers does that problem have? 2. So anytime you take a square root to solve a problem, you have the positive and the negative answer. So we need to remember that kind of thing. The other thing that's going to help us is this diagram. This diagram tells us where each trig function is positive. So if I had something like this, let's say sine of x equals 1/2. There are two quadrants where the sine equals a positive number. What are the two quadrants where the sine is equal to a positive value?
Top two.
The top two.
Wait, how do you? Oh, that's an all inside.
All sine,
But
sorry, that's tangent. And then the lower right is c. So it tells you which trig functions are positive where. So if I use my calculator to solve this, I have to get rid of sine. How do you get rid of sine? Inverse. So if you take the inverse sine of 1/2, yes, that will give you one answer to the problem, which is, what angle do you take the sine of and get 0.5 as the answer? 30. So that is one answer. But there's another angle. In what quadrant would the other answer be in?
the second.
In the second.
Oh,
That's 30 degrees is the first quadrant.
yeah.
So it would be in the second. Now, that's what we call a reference angle. We talked about this before. If you draw a reference angle in quadrant 2 of 30 degrees, it would look like this. The other answer is that. The angle to get all the way to that point in quadrant 2. So what would the other answer be? 150. So does anybody remember the formula in quadrant 2?
180 minus the reference angle.
Yes. In quadrant 2, it's 180 minus the reference angle. In quadrant 1, it just is the reference angle. How about quadrant 3?
180 plus the reference angle.
Yep, 180 plus your reference angle. And what about if you're looking for an answer in quadrant 4?
Minus reference angle.
360 minus the reference angle. And the way you know what quadrant you're looking for an answer in is you're going to look at the original problem. It's going to have a trig function. It's going to be equal to a number. It's either going to be a positive or a negative number. Depending on if they want positive or negative answers, this chart tells you where to go for the answer. And then this chart tells you what to do in that quadrant. So that ASTC chart and this reference angle chart, those are the kind of two important things that we're going to use to solve problems. So we'll try a couple examples. My goal is not to finish this today, but if we start it, we'll definitely finish tomorrow. We might be able to start 8.1, and that'll give us a little bit of a review day on Thursday. So even if we get done quicker, we're not going to do more. We're going to stop whenever we finish 8.1 part 1. All right, so let's look at this one. First thing I notice is it says to only find answers between 0 and 2 pi. So I do not need to worry about a plus 2 pi n on any of these answers. If it didn't have this at the end, then I would. But the problems we're going to do in this section, I don't think any of them you have to put plus the period times n. Okay, so somebody noticed that this looks kind of like a quadratic. The problem with it is it's basically a quadratic that would look like this. It's a quadratic with different variables. One of them is using cosine, one of them is using sine. To solve a quadratic, you need all the same variables. In our case, all the same trig functions.
Sorry, what's at the bottom there? What's that? Oh, alright, so it's a formula to remember.
What is that? It's a Pythagorean identity. So that's a hint at what will help you to get everything in terms of one trig function. So you're going to substitute. You're not going to substitute for the 1. Do you think you're going to substitute for the cosine squared or the sine?
Cosine squared.
Yeah, you always substitute for the one that is squared. So we're going to substitute right there.
Just a second question. Why wouldn't you do the 1?
The 1 is a constant. That's already a pretty simple number. We don't want to change
I'd
that.
just be messing it up.
Yeah, leave the constant alone. Leave the term to the first power alone. Substitute for the thing that is squared. That's pretty much always the rule. So everything else stays exactly the same. Except instead of cosine squared, using your Pythagorean identity, what does cosine squared equal?
Minus sine
Sine
squared.
Minus sine squared x. Okay, now let's do what we got to do and kind of make this look more like a quadratic. What do you have to do with this 2? Distribute. So that's negative 2 sine squared x. I didn't forget about 2 times 1. I'll come back to it. Plus sine x. Now, what's 2 times 1? 2 plus 1 more. 3. Hey, and there you go. That's a quadratic. Now, if we want to try to factor it, this would basically be like trying to factor this problem. I don't like factoring problems like this. What do you think I don't like about this one? I don't like having a negative in front of the quadratic term. I don't mind if there's a negative somewhere else. So what would you do to change this negative to a positive?
Multiply by negative 1.
Yeah, multiply everything by negative 1. And it's just going to change the sign of everything in the problem. Let's do the same thing here. So 2 sine squared x minus sine x minus 3 equals 0. Now, if you can factor this, then you can factor that. It's exactly the same factor. If you want to try the one on the right, we can try that first, but then we have to do it with sine. So if you wanted to factor that, what would be your first term in each parenthesis? Yep. So in our problem, it's going to be like a 2 sine and a sine instead of a 2x and an x. What about your signs inside the parentheses? One's going to be a plus, one's going to be a minus. And what about 2 numbers that multiply to give you 3? 3 and 1. Let's try that. That gives you 2x squared minus 6 plus 1. That's not even close. So let's try switching them. That gives you negative 2x plus 3x, which is how much?
X.
X. So I'm pretty close to factoring it. What do I need to fix?
Sine.
Yeah, just fix the signs. Plus, minus, and now you've got 2x minus 3x is negative x. So that's how you factor that problem. Same thing here. How is the one that I have up above going to factor? 2 sine x. Yep. And what do we do with each of those factors? Set them equal to 0. 2 sine x minus 3 equals 0. Sine x plus 1 equals 0. So what would sine x equal in this case?
which one? Left or right?
This one I haven't filled in.
That would just be, it'd be sine equals negative. So sine equals 3 over 2.
3 over 2. And let's do this one. Sine x would equal negative 1. What's 3 divided by 2?
1.
1.5.
Yep.
When does the graph of sine hit 1.5? Never. So this part has no solution. Doesn't mean the entire problem doesn't have a solution, but this part tells you nothing. Sine of x never equals 3 over 2. How about this part? Think of your graph of sine. Does the sine ever hit negative 1?
Yes.
Yes. Right there. Where does the sine hit negative 1? 3 pi over 2, and it only hits it once. So there is not a second time it hits it between 0 and 2 pi. It hits it again later on, but not between 0 and 2 pi. Let's do these. So that is the answer to that problem. 3 pi over 2, or 270 degrees. No quadratic formula at all. Any question on that? Let's try one more of those.
3 pi over 2, but
Yep. And this will be our last one. So, find all solutions in one period. Well, we'd have to think about that. Period of cosine is 2 pi. The period of sine squared is pi over b. That's your formula. B in this case is what? 1. What's the least common multiple between 1 pi and 2 pi? 2 pi. So we've talked about that, I don't remember when, at some point in chapter 7. So that comes back too. Okay, so least common multiple, 2 pi. So let's find all solutions. Exactly the same as the last problem. Between 0 and 2 pi. Okay, what should we do first to make this problem look more like the last one?
why 3 pi?
We just found the least common multiple of all of each periodic term.
Why this one and not the last one?
The last one they already told me what to do, so I didn't have to worry about it. This one they didn't give me that.
I see. I said it's just finding out what the period is supposed to be.
So what should we do with that to make it look like the last one? Yeah, we got to get it equal to 0. Now, what term did I say I like to have positive?
Squared.
The squared one. Watch what I'm going to do, though. I'm going to bring everything to the right. You might be like, huh? I thought you wanted the squared one positive. I did. Okay, so just put everything on the right. So negative 2 sine squared x plus cosine x plus 1. Okay. Now, what are we going to substitute for? Sine squared. What's the formula or what's the identity we're going to use?
1 times cosine squared.
You remember what's the identity we use?
Sine squared equals sine squared of x equals the cosine squared of x.
Like-
1 minus.
like
Oh,
that?
sorry, it's one minus cosine squared. No, it's cosine minus 1.
It's two different answers.
It's 2 cosine squared.
2
Not
cosine
two, not
squared.
2, I'm sorry. I'm living one thing. What?
1 is cosine squared.
1 minus cosine squared equals sine squared. Any question on that? It's the same one I think we had right here. Well, a little different. We're substituting for the other one. All right, so substitute that in. So -2. And what are we going to put inside the parentheses?
1 minus cosine squared.
1 minus cosine squared. Now maybe you'll see why I brought the cosine squared to the right, because I wanted it to be positive. And now I know it's going to become positive. Because I already knew I was going to be distributing a negative to it. That's why I put it where I put it. If you didn't know that, that's fine. You could put it on the side and then fix it after. So what do we get when we distribute -2 to negative cosine squared?
Just 2 cosine squared.
2 cosine squared plus cosine x. And what about my constant?
It'll just be -1.
So -2 plus 1. Okay, let's see if it factors. What would be my first term if this is going to factor? 2 cosine x. Second term? Cosine x. What about my sines? I need a plus and a minus. And I really don't have much choice here. 2 numbers that multiply to give me 1. Let's see, does that work? 2 cosine squared. That gives me plus 2 cosine x minus 1 cosine x. Is that what I want in the middle? Oh, Eric?
Probably not. I don't know. It would give you what? 2 cosine x? That's not what you have.
Yes.
So if we FOIL this out, do we get the term I want in the middle?
2 cosine x times 1 is 2 cosine x
So that's 2 cosine x
minus cosine x.
minus cosine x.
That's just cosine x.
6 cosine x.
Yes.
So what do we do with each one of those?
You break them apart to kind of see.
Okay, so with the first one, cosine x is going to equal
1 half.
1 half. And cosine x is going to equal
-1.
-1. Now, when it's equal to 1 or -1, you can just think about the graph. You don't really have to use the calculator. Where does cosine hit -1? Pi. So there's your first answer. And does the cosine ever hit 0.5?
Yeah.
Yes. How am I going to get rid of cosine?
Inverse cosine.
Inverse cosine of a half. Let's do it in degrees first, because if you're going to get a nice answer, it'll be in degrees. And you do get a nice answer of 60. And 60 is what in radians?
5/3.
Yeah, pi over 3. Now, we were looking for where the cosine equaled a positive number. Put this right here. We have one answer. 60. Where is 60? Quadrant 1.
Yeah.
So we got that. Where else does cosine equal a positive value?
4th quadrant.
4th quadrant. This is my reference angle. What's the formula to find an answer in quadrant 4?
360 minus the reference.
360 minus the reference angle. So what's 360 minus 60?
300.
300. Or, well, that's just times 5 to get to 300.
5/3.
So 5 pi over 3.
Wait, sorry, why didn't we do cosine x -1? Or did we? Oh, we did, okay. So
We did take the inverse cosine to get one of the answers, but the calculator is not going to give me the other one. And you can check it. Type in the cosine of 300. You get 0.5. Type in the cosine of 60. 0.5. There's the two answers that will come out to 0.5.
Right, so are there three answers? Is there one for the cosine x equals -1?
Yep.
Is that a zero?
180.
Yeah.
That was the easy one because I didn't really, because it was equal to -1, I just had to think where cosine hit the lowest. Okay, any question on that? That's pretty much all of it when you're doing factoring. Quadratic formula, a little bit different, but if you know how to do it with regular algebra equation, doing it with a trig equation, same thing. All right, so let's I'm gonna change that a little bit. All right, now some of these problems, like 1 through 6, like this is question 1. It's not as complicated as factoring. To solve question 1, you just need to take the inverse sine of both sides and then find the second answer using the ASTC. So questions 1 through 6 are all like this. Just a trig function equals a number. That's basically like where we were when we got to this step right here. It's like they're starting you at that step. In questions 7 and 8, they're starting you at this step. So they realized that it was a problem that could be factored. They do the factoring for you. And then they write something times something equals 0. So your job from there is to split it into two problems and then solve it. But you don't have to do the factoring because it's already taken care of. So I think that's what we'll do. So we'll do 1 through 10 on that page. So all the factoring is going to be done for you. And then those 5 questions from the other page.
Alright, is this 423 still?
One page is 423, the other one is 417.
Oh wait, so it's just 1 through 10.
1 through 10.